Hello and welcome, dear students. The title of today's topic is Tides, Mechanism and Types. The various movements of the ocean include waves, tides and currents. They occur both at the surface and in the deep sea and play a vital role in how our planet functions. Tides are the ocean's heartbeat. Tides are the most fundamental, reliable and spectacular movement of the sea. The slow, massive daily rise and fall that completely changes the coastline. Each day, the sea level rises and falls, causing the shoreline to shift back and forth. This natural cycle is why sand castles built at low tide often vanish as the water returns. But what actually causes billions of tons of water to move? It is not the wind, it is the moon's gravity. This lecture will dive into the incredible celestial mechanics that generates these forces, explains why your local high tide is always 50 minutes later each day, and show you how these forces combine to create the most extreme high and low tides on the planet, known as spring and neap tides. By exploring this topic, you will learn about the different types of tides, the gravitational mechanism that controls them, and the various tidal patterns observed around the globe, as well as their overall importance in the field of oceanography. Now, coming to the main topic, tides. The rhythmic rise and fall of the ocean. The rhythmic rise and the fall of the ocean's surface is known as tides. This process is a constant cycle along our coastlines. The water gradually climbs the shore until it reaches its peak called high tide, before slowly receding to its lowest point known as low tide. These movements are primarily driven by the gravitational pull of the moon as it acts upon the earth and its massive bodies of water. Because the moon is relatively close to our planet, its gravity is strong enough to stretch the oceans, creating the bulges of water that we experience as tides. Moon's influence. Although both the sun and the moon exert a gravitational force on the earth, the moon's influence is dominant. This is because gravitational force depends heavily on distance. Since the moon is much closer to the earth than the sun, its pulls on our oceans is roughly twice as strong as the sun's. Now, regarding the two bulges. This gravitational interaction causes the ocean water to stretch, creating two distinct bulges on the planet. The first one is the direct bulge. One bulge forms on the side of the earth closest to the moon, where the moon's gravity pulls the water towards it. The next bulge is known as inertial bulge. A second bulge forms on the side of the earth farthest from the moon. This occurs because of the inertia or centrifugal force generated as the earth and the moon orbit their common center of mass. As the earth rotates on its axis, every 24 hours, coastal locations pass through these two bulges, creating the daily cycle of high and low tides. Now, we will discuss about the types of tides. Effects of rotation, revolution and declination of Earth, Sun and Moon produces short-term and long-term variations in tides. Let us now get familiar with these variations and resultant tides. They are daily variations, fortnightly variations, monthly variations, yearly variations and long-term variations. Now, let us discuss them one by one. Daily variations. Based on the tidal frequency in a day, three types of tides have been observed in the different parts of world. The first one being the diurnal tides. When tides occur at an interval of 24 hours and 50 minutes, they are called diurnal tides. One high tide and one low tide takes place with a daily periodicity of 24 hours 50 minutes in high latitudes. The second is the semi-diurnal tides. When tides occur at an interval of 12 hours and 25 minutes are called as semi-diurnal tides. Two high and two low tides occur after 12 hours and 25 minutes and they are found in low latitudes. Mixed tides. They are the most frequent of tides, especially in mid-latitude regions where high and low tides alternate with unequal wave height and period. The second is the fortnightly variations. The moon completes one cycle around the earth in 29.5 days. The position of the earth also changes with respect to different phases of the moon. Thus, the moon's tidal forces varies in the following manner in a month. Number 1 is the spring tides. Twice a month during the new moon and the full moon, the earth, sun and the moon align in a straight line. This specific alignment is known as SYZYGY pattern. Because the gravitational forces of the sun and moon work together in this position, they create significantly higher tides, often nearly 20% above the average level. These are known as spring tides. During a new moon, the sun and the moon are positioned on the same side of the earth, a setup called conjunction. In this phase, the moon sits directly between the sun and the earth. If the moon perfectly blocks the sun's light and casts a shadow on our planet, it results in a solar eclipse. When the earth is positioned between the sun and the moon, the alignment is called opposition. This occurs during the full moon phase. If the earth blocks the sunlight from reaching the moon, leaving it in a darkness, a lunar eclipse occurs. Neap tides. When the moon reaches its first and third quarter phases, it moves into a position that is perpendicular to the sun relative to the earth. This 90-degree alignment is known as quadrature. During this time, the gravitational forces of sun and the moon pull from different directions and essentially work against each other. As a result, the tidal bulges are much smaller because the sun's gravity offsets some of the moon's pull. This occurs twice a month, roughly 7 or 8 days after the new and full moon phases. Now, the third one is the monthly variation. You know it very well that moon is revolving around the earth on an elliptical orbit. In each synodic month, average of which is 29.53 mean solar days or about 13 hours and 44 minutes, distance between the earth and the moon on the elliptical plane becomes the smallest and largest. Now, perigean tides. As the moon revolves around the earth on an elliptical path, its distance varies from the earth. At perigee, the moon is closest to the earth, around some 3,56,000 km, and this accounts for greater gravitational force. Therefore, the tide during this time is very high. It is higher than the normal tide, almost around some 15 to 20% higher. Another are the apogean tides. At apogee, moon becomes farthest from the earth once in a month, that is nearly about some 4,07,000 kilometers, which accounts for lower gravitational force as compared to the perigee. Hence, Apogeian tides are 20% lower than the normal tides. Now, another type of variation is known as half-yearly variations. Declination of sun varies from 0 degree around at equator to the maximum at 23.5 degree north and south in different seasons. Declination of a celestial body is its angular distance from the celestial equator on a celestial sphere. Tilt of Earth's axis and declination of the sun produces half-yearly variation in tidal force in each hemisphere, and the resultant tides are formed. For example, the equinoctial tides. During both spring and autumn equinoxes on 21st March and 23rd September respectively, sun's rays are overhead at equator, due to which tidal bulge at equator becomes stronger and the resultant tides are called as equinoctial tides. Solstice. During winter solstice 22nd December and summer solstice 21st June, sun's rays are overhead at Tropic of Capricorn and Tropic of Cancer respectively. Hence, tidal bulge gets tilted in the direction of the maximum declination of a sun twice a year. Now, yearly variations. While revolving around the sun, variation in distance from the earth results into larger and smaller solar components of tidal force, and the following tidal result. Number 1 is the perihelion. On January 3, when earth comes closest to the sun around some 147 million kilometer, tide generating force is relatively high and hence bigger tide is recorded. Aphelion. On July 4, earth is the farthest from the sun around some 152 million kilometer and the tidal force is lesser in comparison to perihelion. It results in relatively smaller tide during this time. Long term variations. Besides declination and revolution effects, axis of rotation of earth and moon also proceed after 15.6 and 8.8 years respectively, whereby a perfect alignment condition reaches after a long gap. Absolute maxima reach once in about 1600 years when earth, sun and the moon are in conjunction and moon is in perigee, sun is in perihelion and the axis intersect with the zero declination. Now, we will discuss about the tide generating forces. Newton showed that the gravity and the motion keep celestial bodies in orbit. The earth and moon do not move independently, instead they rotate around a common center of mass called as barycenter, which lies about 1700 km below earth's surface. Because earth is much heavier than the moon, while the moon around the sun, earth also makes a small motion around the barycenter. Although earth and the moon attract each other, their forward motion combined with the gravity prevents collision and keeps them in stable orbits. The same gravitational force acting on earth's ocean are responsible for the formation of tides. Gravitational and centripetal forces in the earth-moon system. To understand tides, we first examine gravitational and centripetal forces in the earth-moon system. Gravitational force. According to Newton's law of universal gravitation, every object with mass attracts every other object. An object can be as small as an individual atomic particle or as large as sun. The gravitational force is directly proportional to the product of the masses of the two bodies and is inversely proportional to the square of the distance between the two masses. Note that g is the gravitational constant, so it does not change. Now, there are certain key ideas you should remember regarding the tides. If mass increases, gravitational force also increases. If distance increases, gravitational force sharply decreases. Doubling the distance reduces gravity to 1/4. Certain facts regarding the variation of lunar gravity, or we call it as the moon's gravity. On the earth, the moon's gravitational pull is not equal everywhere on earth. It is strongest at the zenith point and closest to the moon, and weakest at the nadir point farthest from the moon. Gravitational forces act at slight angles at different places on the earth. This unequal pull plays an important role in tide generation. Now, centripetal forces and orbits. Centripetal force is an inward force that keeps an object moving in a circular path. In space, gravity provides centripetal force. It keeps the moon in orbit and earth. If centripetal force disappears, the object moves in a straight tangent path. Now, tidal bulges and the moon's effect. To understand tides, it helps us to imagine an ideal earth and ideal ocean. In this model, earth has two tidal bulges caused by the moon, one facing the moon and one on the opposite side. The ocean is assumed to be of uniform depth and free of friction, similar to the simplifications used by Newton. In reality, most experiences high tides every 12 hours and 25 minutes. This happens because tides follow the lunar day, not the solar day. A lunar day is about 24 hours 50 minutes, which is 50 minutes longer than the solar day. During one Earth's rotation, the moon moves eastward in its orbit, so Earth must rotate an extra 50 minutes for the moon to return overhead. As a result, high tides and the moonrise occurs about 50 minutes later each day. Now, regarding the tidal bulges and the sun's effect. The sun affects the tides too, like the moon. The sun produces tidal bulges on opposite side of earth, one oriented towards the sun and one oriented away from the sun. These solar bulges, however, are much smaller than the lunar bulges. Although the sun is 27 million times more massive than the moon, its tidal generating force is not 27 million times greater than the moon's. This is because the sun is 390 times farther from the earth than the moon. Now, we will discuss about the earth's rotation and tides. The tides appear to move water in towards the shore, the flood tide, and to move water away from the shore, the ebb tide. How do tides vary during a monthly tidal cycle? The monthly tidal cycle is 29.5 days because that is how long it takes the moon to complete an orbit around earth. During its orbit around the earth, the moon's changing position influences tidal conditions on earth. The monthly tidal cycle. During the monthly lunar cycle, the moon changes phases. At the new moon, the moon lies between the earth and the sun and is not visible at night. At full moon, the moon is opposite the sun and appears fully illuminated. A quarter moon occurs when the moon is at right angles to the sun and appears half lit. When the sun, moon and the earth are aligned during the new moon or the full moon, their tidal force combines producing spring tides with very high tides and very low tides. The alignment is called as SYZ-GY pattern. Spring tides occur roughly every 2 weeks, coinciding with the new and full moons. About 1 week after each spring tide, the system shifts into a neap tide. This pattern follows the moon as it progresses through its waxing, growing and waning or shrinking phases. An interesting feature of our lunar neighbor is that we always see the same side of the moon from the earth. This happens because the moon's rotation on its axis takes the same amount of time as its orbit around our planet, a phenomenon as synchronous rotation. Now, we will come to the another important topic, that is known as theories of origin of tides. 4 most popular theories of tides have been discussed. The first theory is the equilibrium theory. The equilibrium theory explains tides by balancing gravitational and centrifugal forces in the Earth-Moon system. It assumes Earth is mostly covered by water, oceans are fully connected and seawater can move freely. A tidal bulge forms towards the moon due to gravitational attraction opposite the moon due to the centrifugal forces. At locations perpendicular to the Earth-Moon line, near the poles relative to the bulges. These forces balance towards Earth's center, producing low tides. According to this theory, all places on the same meridian beneath the moon should experience tides at the same time. Now, the second theory is the dynamic theory. Laplace in 1755 presented a mathematical explanation of tidal waves after taking into account both vertical and horizontal movements of water. As the earth rotates, tidal bulge generated by gravitational forces starts moving horizontally towards the side of the ocean facing the moon and thereby giving rise to the bulge of water. Thereafter, as a result of pressure gradient, it moves in opposite direction and that gets further deflected by Coriolis force, and thus a bulge with tilt is formed on the side opposite to the moon. Now, another theory is the progressive wave theory. William Whewell in 1833 explained that tides occur at different times on the same meridian due to the progression of the tidal waves, which is generated in oceanic processes and circulations in the Southern Ocean. G.B. Airy in 1842 also expressed a similar views about tides. According to this theory, tides originating under the gravitational force of the moon in the Southern Ocean take the form of primary waves. Time lag due to the progression of this wave accounts for the differences in timings of tidings on the same meridian. Now, finally, the stationary wave theory. R.A. Harris put forward his theory to explain the local differences in timings and types of tides. Once oscillation in a water is set by tide producing forces, then water starts moving in the Earth's ocean like in a big tank. It results in amphidromic points around which water oscillates, and water movement is nil in the center. This is called a nodal point, which has zero wave height, just like the middle point in the seesaw swing. From here, water moves to a maximum level, which is called the antipodal point. Once equilibrium is established, water moves up and down diagonally in the open ocean. Amplitude and timings of the tide are affected by the local phenomena like depth of ocean, coastal and bottom topography, resulting into several amphidromic points in Earth ocean. Now, we will finally discuss about the importance of tides. Because tides are driven by the precise position of the Earth, Moon and the Sun, they can be predicted accurately far in advance. This predictability allows sailors and fishermen to plan their schedules with confidence. Navigation. Tidal heights are critical for coastal safety, particularly for harbors located near or estuaries. High tides raise the water level near the coast, allowing heavy ships to reach the harbor safely. Tides help in fishing also. As the water rises towards the shore, it brings a higher concentration of fish with it, allowing fishermen to secure a much larger catch. Tides help also us in desilting. The powerful movement of tidal water acts as a natural cleaning system. As the tide recedes, it helps flush out sediments, desilting and carries polluted water away from river estuaries into the open ocean. Tides are also useful in energy production. Tides are also a source of renewable energy. By capturing the energy from moving water, we can generate electricity. For example, a 3 megawatt tidal project was established at Durgadwani in the Sundarbans of West Bengal to harness this natural force. This was all about today's lecture. Hope you have enjoyed it well. Thank you for watching.